Everybody, today we have a problem from the NIMO competition, which is no longer in existence as far as I know. Now, this very first problem, we're looking for positive A and B. We have positive A and B, and we have two given equations, and we're supposed to evaluate a to the 6 plus b to the 6. Now notice this very first step here was motivated by the fact that this expansion, a cubed plus b cubed quantity squares, involves something that's given to us. Now again, it's common on these problems to shy away from directly solving for a and b and then substituting into here. It looks like it's possible here, but there's usually more algebraic ways to do it that minimize the arithmetic computations. Okay, now, so we are looking to come up with a number for a to the 6 plus b to the 6. So just rearranging this expression, we get a to the 6 plus b to the 6, what we're looking for, algebraically isolated. But notice we know this much already. Okay, this number here would be what, 16, minus 16? Okay, so all we have to do is find a cubed plus b cubed. All right, and that's what this next bit of algebra, which is slightly more involved than what we just did on the previous step, but we're trying to figure out what a cubed plus b cubed is by working with our other given. This is our other given. We've already used this given in a manner of speaking. So let's see what we can get from this. And again, the algebra is not difficult. This part right here is just a common denominator. And then ironically, you don't, when you expand this out, you get these four terms here. Okay? But notice that AB is present like all over the place, right? And so when you substitute AB equals to 2 into the appropriate spots, this is the expression you get. And lo and behold, we have a cubed plus b cubed sort of isolated in both the numerator and the denominator of the fraction on the left-hand side. Okay? So now notice here that if we tried something kind of obvious, like if we tried a cubed, let me just write this over here. It's tempting to check out a cubed plus b cubed equals 3. But if you do that, that implies 7 over what? If you put 3 right here, this would be 7 over 9, right? So you get the 7 that you want, but then you get 9, right? Again, if you try the obvious, a cubed b cubed equals to 3. Let me write the 3 right here. That implies this fraction would be 7 over 9. Again, if you put a 3 right here, you do get 7. If you put 3 right here, you get 9, right? Okay, so it turns out you have to, it's not equal to 7 over 8, but it would have to equal some multiple of 7 over 8. Not a multiple, but an equivalent fraction. So 14 over 16 is an equivalent fraction, right? Different name for the same fraction. 14 over 16. And you can see quickly here that a cubed plus b cubed would have to be equal to 10 to take care of business on this. A cubed plus b cubed by inspection is equal to 10. And again, folks, hope that was clear. We tried the obvious a cubed plus b cubed is equal to 3, but we didn't get 7 over 8 when we did that. We got 7 over 9. So it makes sense to consider the equivalent. This is not a multiple. This is just an equivalent fraction. You multiply the numerator by 2, denominator by 2, and you get 14 over 16. And notice that gets what we want. If there's a 10 here, that's 14. If there's a 10 here, that's 16. So we get that a cubed plus b cubed is equal to 10. So we can come up here. We're interested in a to the 6 plus b to the 6. So what we end up with is this is equal to 10 squared. Right, I put 10 right here. So we get 10 squared minus 2 times 8, which is 16. Right, is that 100 minus 16? That's equal to 84, which is the answer. And again, y'all, it was the algebra that did everything for us. It was a little, some of it was a little sneaky to find. This part here about trying an equivalent fraction is a little sneaky. You might be, I almost gave up when I saw that 3 didn't work. And I realized, wait a minute, you can write an infinite number of equivalent fractions here to maybe get a solution. And it turned out the second one, if you want to call it that, got us the solution. So the answer is 84. Now, just last comment here. It doesn't look remarkably difficult to try to solve for A and B here. You're going to get to, it'll be a quadratic form, it looks like, and then you'll end up with maybe, I'm not sure, you could end up with two solutions, but they'll work out in a symmetrical sort of fashion, you know. So in other words, you could try B is equal to 2 over A right here, right? And what would you get? You would get 4 over A squared. And then something similar over here, and you might get something that works out okay. I'm not certain. But in any event, there's that is a try, but it's kind of an inelegant approach. The algebra here, which was fairly highly motivated in my opinion, it works out nicely. This is an easy step to see. This step was slightly more, you know, because you might think, you know, there's ways you could go wrong here. I think it's a little bit more of a slippery slope here, in my opinion. Although it's not difficult. It's not particularly difficult. But anyway, 84 is the final answer. Thank you for viewing. And let me know if you know anything about NIMO. It stands for National Internet Math Olympiads. Evan Chin, David Altizio, some other real math comments were involved in this. And I just think it kind of dissolved. I don't think there was enough administrative resources or enough interest to keep it alive. I don't even know how long it came into existence. But there's a plethora of nice problems that were either written for this and or appeared in these exams. Okay, and I'm pretty sure Altizio wrote quite a few of them. This is one of his. But anyway, that's it. Thanks for viewing.